Quantum supremacy, is the threat real? What is quantum supremacy and why it sounds scary? Quantum supremacy refers to the point where quantum computers outperform classical ones at specific tasks. While this sounds abstract, the potential consequences are very real, especially for cryptography. Quantum algorithms like Shor's could in theory break RSA and elliptic curve cryptography, ECDSA, the backbone of Internet security. Grover's algorithm can also weaken symmetric encryption by reducing brute force resistance. Because cryptocurrencies like Bitcoin and Ethereum rely on ECC, e.g., ECDSA for digital signatures, they often get singled out as vulnerable targets in media coverage. CEG Wired's "The Quantum Apocalypse is Coming. Be very afraid," but the fear extends far beyond blockchains. If a capable quantum computer existed today, it wouldn't just break wallets, it would compromise banks, military networks, and state secrets. There is another serious vector known as harvest now, decrypt later, HNDL. Adversaries today are hoarding encrypted data, such as personal, government, or corporate information, that's unreadable now, and thus not even considered as a leak, but it may be breakable in 5 to 15 years once quantum computers reach sufficient power. In other words, huge volumes of data that seem secure today could suddenly become exposed, not because it was hacked in the future, but because it was stolen and patiently stored until quantum decryption becomes feasible. Intertemporal hacking based on technological expectations becomes a reality. In other words, quantum computing is a threat to the entire internet, not just Bitcoin. Where the threat actually stands. Despite headlines warning that quantum is coming, the actual machines are nowhere close to what's needed to threaten cryptographic systems. Today's quantum computers have fewer than 1,500 error-prone qubits. Breaking something like Bitcoin's ECDSA would require millions of stable, fault-tolerant qubits, well beyond current capabilities, as shown in recent analyses by cryptographers and Microsoft Research. Experts like Peter Weyl and Daniel J. Bernstein agree, quantum risk is long-term and theoretical. For now, progress will likely be incremental with many signs and warnings before anything existential emerges. Meanwhile, the solution space is advancing rapidly. In 2024, NIST finalized its first post-quantum cryptography (PQC) standards, FIPS 203-205, covering lattice and hash-based schemes. Global agencies and academic communities are already building software libraries and tools for post-quantum migration. How major protocols are responding. The crypto world is not waiting passively. The leading protocols are already hardening against quantum threats or preparing upgrade paths. Bitcoin uses hashed public keys by default, P2PKH, meaning the public key is not revealed until coins are spent. This gives quantum adversaries only approximately 10 minutes to attack during the mempool phase, a time frame that's practically impossible with foreseeable machines. Here is a great recent coverage on post-quantum HD wallets, silent payments, key aggregation, and threshold signatures in Bitcoin. Ethereum is moving heavily into zero-knowledge proofs, which not only enhance privacy and scalability, but are also more adaptable to post-quantum cryptography. Projects like ZKSYNC, Polygon ZKEVM, and Scroll are already experimenting with quantum-friendly snark schemes. Vault 12 crypto inheritance, built on Shamir's secret sharing, is already quantum-resistant by design. It doesn't rely on factorization, elliptic curves, or any number-theoretic assumptions. Instead, it uses information-theoretic security. Without enough shares, no amount of classical or quantum power can recover the original secret. Together, these protocols cover the most critical crypto infrastructure for payments, smart contracts, and long-term value protection. And all three are on track to remain secure even in a post-quantum world. Why Shamir's secret sharing doesn't care about quantum computers. Shamir's secret sharing, SSS, divides a private key into multiple parts, requiring a threshold number to reconstruct it. A user might, for example, split a secret into 5 shares, with any 3 being sufficient to restore it. The key strength of SSS lies in its information-theoretic security. Below the threshold, the remaining shares offer zero information about the secret. No brute force, no math trick, and no quantum algorithm can infer the key. As documented by academic cryptography, this places it entirely outside the attack range of Shor's or Grover's algorithms. This makes crypto inheritance by Vault 12 a rare example of a real-world product that is already secure against future quantum threats. It's not waiting for standards, patches, or forks. It's not adapting, it's already built on quantum-immune primitives. If more protocols adopted Shamir-like information theoretic guarantees, the urgency of the quantum threat would drop significantly. Panic is optional, preparedness is real. Quantum supremacy is a fascinating long-term challenge, but it's not a reason to panic. The cryptographic world, academic, governmental, and decentralized, is actively preparing. Bitcoin, Ethereum, and crypto inheritance by Vault 12 each represent distinct efforts toward quantum resilience. Bitcoin is advancing toward post-quantum safety through stealth wallets, key aggregation, and threshold signature schemes. Ethereum explores ZKPs and quantum-compatible primitives. Vault 12 offers a native solution using mathematically unbreakable secret sharing. If the quantum future arrives, these protocols will be ready. Some, like crypto inheritance, already are.